Hello, chemists and biochemists. In this video, what I'd like to talk to you about is calculating the charge of a single amino acid. Now, this is going to show that most amino acids, well, they really don't have that many charges or possible charges. But let's go ahead and get started. Now, what I always like to do is I like to think about my amino acids as falling into a couple of different categories. If they are a nonpolar amino acid, for instance, leucine or valine, isoleucine, well, I know that those R groups are really just a bunch of carbons and hydrogens. The amino acids that I'm concerned with and mostly interested in when it comes to calculating the charge are my positively charged amino acids and my negatively charged amino acids, which really boils down to a total of 5 amino acids. I'm concerned with lysine, which I'm going to represent these amino acids by their 3-letter codes. LYS, lysine, arginine, ARG, histidine, HIS, and aspartic acid, ASP, and glutamic acid, GLU. So these two down here are my negatively charged amino acids, and these 3 up top are my positively charged amino acids. Now, I'll use lysine as an example. Lysine, which I'm going to now represent by its single letter code for K. What I always like to do is I like to imagine that where I've placed my letter, I have a total of 4 different sides. Here, 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 and here. Now, the top side is where whenever I'm drawing this molecule, I will put my hydrogen that comes off of my alpha carbon. The right side of my molecule is where I'm going to put my carboxylic acid, my first or one of my ionizable groups. Down at the bottom is where I'm going to put my R group. And then to the left-hand side of my letter K there is where I put my amino or my NH3 functional group. Okay, so I just want to give you a little bit of a sense of how I approach this sort of problem and how I approach this sort of question. Now, what I'm going to do is I'm going to write for each of those different kind of mapped out groups, what are the pKa's associated with them? The N-termini for lysine has a pKa of about 8.95. The R group for lysine has a pKa of about 10.53. The C termini has a pKa of about 2.19. Carboxylic acid, an amino, and another amino functional group. So we've got 2 basic groups and then 1 very acidic group. Now, what I need to know about these groups is that my amino group is positively charged, my R group is positively charged, and my carboxylic acid has no charge. Well, this is all dependent on what pH is my molecule in. Now, if I said that this molecule was in a pH of 1, all of those statements that I just shared about those charges would be true and accurate. If I said the solution pH was 4, these charges that I identified would not be true. The reason they would not be true is, well, specifically looking at the C termini of this lysine, a pKa of 2.19, well, what we always want to do is think about pKa versus pH. The pKa is something that is true of that molecule. That pKa is, for the most part, not going to change unless it's interfered with in some form or fashion. But that pKa is true to that molecule. It's kind of like a personality trait almost. So my pKa, when it is less than my pH, that means the group is deprotonated. Now, when my pH is less than my pKa, so when my pKa is greater than the pH, what that means is that my group is protonated. So as an example of that, when I said my my solution was pH of 1, and my C-terminal group, my carboxylic acid, with a pK of 2.19 was protonated. That all is true. Okay, now The way that I kind of approach these and what you really need to know is what these functional groups are capable of. A carboxylic acid, for instance, is going to either be neutral or -1. An amine is either going to be neutral or +1. None of these groups are going to be -2, and they're not going to be +2. They're not going to, they're fairly simple. They're either going to be protonated or deprotonated, and they're either going to be positively charged or negatively charged. Now, carboxylic acid, when it is protonated, has no charge whatsoever. So make sure that you don't think protonation means charge, positive charge. It does not necessarily. You have to think about the group that's involved. So if I were to look at this sort of question, or if I were to look at, well, what is the charge of, let's go with lysine, K, at pH equal to 9.9. Okay, in that case, what I would do is I would say, here is my lysine at a pH of 9.9. What is that? 9.9 is greater than 2.19. Okay, so that means that this group on the right-hand side, my carboxylic acid or my carboxylate ion, is going to have a negative charge because it's gone from having no charge to negative because my pH is greater than my pKa. My N-terminal, the left-hand side of my molecule, what I've drawn, well, that has gone from positive to what? Well, when my pH is again greater than my pKa, that group is going to be deprotonated. So that's going from a positive charge to no charge whatsoever. My R group, on the other hand, my R group has a pKa of 10.53. 10.53, the pKa is greater than my solution's pH of 9.9, meaning this will have a positive charge. So all that amounts to, at a pH of 9.9, lysine, the predominant form of lysine in the solution, will have a charge of, let's see, negative and a positive. Those will cancel out. My third ionizable group will have no charge whatsoever. The predominant form will have a charge of 0. Well, there's also the possibility that the -1 form could be in there, but it's at a lower concentration. All right, well, if you remember, pKa less than pH means deprotonated. pKa greater than pH means protonated. That's going to help you out tremendously. All right, well, I hope you had a good one. I hope this helped your understanding of how to calculate the charge of an amino acid. Have a good one.